All right, so let's jump into this. You sent over some fascinating research about a new approach to nearest neighbor search and how it's shaking things up in retrieval augmented generation. I know you're already deep in vector embeddings and AI content generation, so we need to get you the inside scoop.
Absolutely. And it all starts with understanding how we search for similar items in massive amounts of data. That's where nearest neighbor search comes in, a fundamental algorithm used not just in AI, but in recommendation systems, image recognition, you name it.
Okay, so nearest neighbor search is like finding a needle in a haystack,
Yeah,
but on a massive digital scale.
exactly. Imagine trying to find a specific product in a huge online catalog or a document that matches a user's query. Now think about the computational resources needed to do these searches efficiently. That's where algorithms like HNSW come into play. Hierarchical Navigable Small World.
So you've been working with HNSW for a while now, right? Can you break it down for us? What makes it so special?
Yeah, it's been a workhorse for a lot of us. Think of HNSW as a multi-level library, with each level organized, containing progressively fewer books. But those books are increasingly relevant to your search topic. As you navigate the levels, you quickly narrow down your search space, leading you to the most similar items, those nearest neighbors.
So HNSW helps us find those needles in the haystack faster by creating a clever, organized system, like a super efficient library.
Exactly, and this has been crucial for applications like RAG, where we use vector embeddings to represent chunks of text. These embeddings are like coordinates on a map, and HNSW helps us locate the most relevant chunks based on their proximity in this high-dimensional space. Think of it like this. You're using vector embeddings to represent chunks of text that you're feeding into your RAG system. HNSW is that organizational structure that allows you to find the right chunks quickly and efficiently.
It's like having a librarian who instantly knows where every book is, even in the largest library imaginable. But the research you sent suggests there might be an even better way, this flat approach.
That's where things get really interesting. This new research challenges the assumption that we need a hierarchical structure like HNSW for efficient nearest neighbor search. They call this new approach FlatNav, and it uses a flat graph structure, like spreading all those books out on a single massive table.
Hold on, a flat structure. How can that possibly be as efficient
Hmm.
as a multi-level library system? Wouldn't that make the search chaotic?
That's what I thought too. But here's the thing. This research suggests that in high-dimensional data, like the kind you deal with in RAG and vector embeddings, there's an inherent structure. That makes hierarchical approaches less necessary. They call it the hub-highway hypothesis. Imagine certain books on that massive table being super popular, with people constantly referencing them and connecting them to other books.
So these popular books become like hubs, with paths leading to other relevant books, creating a network of interconnected information.
Exactly, like those bustling airports that serve as central hubs, with flights connecting to various destinations. In high-dimensional data, certain data points naturally become these hubs, appearing in the nearest neighbor lists of many other points. These hubs form natural highways that allow searches to efficiently traverse the data space, even without a hierarchical structure.
Okay, so instead of building a multi-level library, we're discovering that the books themselves, through their connections and popularity, have already created a system of highways and hubs that we can navigate.
Precisely. And the exciting part is this flat nav approach. By ditching the hierarchy, uses significantly less memory. Imagine the difference in space requirements between a sprawling multi-level library and a single massive table. This memory efficiency has huge implications, especially for ARGI systems dealing with tons of data.
So less memory, potentially faster searches, all by embracing the natural structure of the data itself. This sounds like a game changer.
It has the potential to be. And it makes you wonder if we've been overthinking things, imposing artificial structures, when the data might be whispering its own elegant solution all along.
This is mind-blowing, but before we get too carried away, let's break down the specifics. How exactly does FlatNav work? And what are the implications for someone like our listener, who's deep in the world of RAG and vector embeddings? Let's unpack that in part 2 of our deep dive.
It's fascinating how this seemingly simple shift from hierarchy to flatness can have such profound implications.
Yeah, it really is. It's almost like nature is showing us a more efficient way to
Well,
organize
Yeah.
and navigate complex information.
And the researchers, they didn't just propose this hub-highway hypothesis, they actually did experiments to validate it. They analyzed how searches navigate through data, tracking which points are visited most frequently.
So they're like traffic engineers, observing the flow of data and identifying those busy intersections and popular routes.
Exactly. And what they found was the distribution of visits was far from uniform. Certain data points, those hubs, were visited way more often than others, just like certain airports or train stations handle a ton of traffic.
So these popular hubs are like the grand central stations
Yeah.
of our data,
Yeah.
connecting different regions
Yeah.
and allowing us to quickly traverse vast distances.
Precisely. And they found that these hubs weren't randomly distributed, but were also more interconnected than other data points, forming those efficient highways we were talking about.
So we have scientific evidence supporting this hub highway concept.
Yeah.
But let's get practical for a second. You mentioned RGA, but how does this flat nav approach impact real-world applications?
Well, the potential applications are huge. Imagine you're building a RAG system to power a chatbot. For a massive e-commerce site with FlatNav, your chatbot could access a much larger product catalog without sacrificing speed or blowing up your server costs. Instead of relying on a complex hierarchy to find similar products, it could leverage the natural connections and popularity of products to navigate the data quickly.
That makes sense.
Yeah.
And it's not just limited to chatbots, right? Any application that relies on finding similar items in a large data set could benefit from that.
Absolutely. Think about image recognition, where you're searching for visually similar images from a massive database, or in drug discovery, where researchers are looking for molecules with similar properties. The ability to handle larger data sets with less memory opens up some really exciting new avenues for research and development.
So it's not just about speed and efficiency. It's about pushing the boundaries of what's possible with AI by reducing those computational bottlenecks.
Exactly. And it's important to note that this research, it's still pretty early. The authors acknowledge that. FlatNav, as it stands now, is more of a research prototype. There's still room for optimization and further development.
So this is just the beginning. We're witnessing the early stages of a potential paradigm shift in how we think about searching and organizing data.
I believe so, the hub highway hypothesis. And this FlatNav approach, they really challenge us to rethink those fundamental assumptions about how we structure data. It suggests that sometimes the most elegant and efficient solutions lie in embracing the inherent structure of the data itself.
It's almost like we're learning to listen to the data, to understand its natural patterns,
Flow.
instead of imposing our own rigid structures.
And as the volume and complexity of data continues to grow, this ability to listen to the data will become even more crucial. For our listener who's working with ARIA and vector embeddings, this research offers valuable insights and potential advantages.
Absolutely. So let's distill those insights. What are the key takeaways for someone who is deeply immersed in this world? What should they be thinking about as they continue to build and experiment with these technologies?
Well, first and foremost, I think, this research is a call to action. If you're building with RGAG or working with vector embeddings, experiment with FlatNav. Don't be afraid to ditch the hierarchy and see what happens. You might be surprised at the results, especially in terms of memory efficiency and the ability to handle larger data sets.
So embrace the flatness, don't be afraid, to challenge the conventional wisdom of hierarchical structures.
Exactly. And secondly, remember the hub highway hypothesis. It's a really powerful concept that can change how you think about navigating. High-dimensional data, those hubs and highways, they exist within your data, waiting to be discovered and leveraged for more efficient search and retrieval.
It's a reminder that sometimes the most efficient path isn't the one we create, but the one that already exists within the data itself. This is powerful stuff. But I have a feeling there's even more to unpack here. Let's continue our deep dive in part 3, where we'll look at the specifics of FlatNav performance and what the future might hold. For this exciting new approach, it's like we're switching from a meticulously planned city grid to a more organic, interconnected network of paths and hubs.
I like that. And the research shows some pretty compelling results. They tested FlatNav on the Big N dataset, a massive collection of 100 million data points, and compared its performance to HNSW.
That's a serious stress test. What did they find?
Well, FlatNav did really well, achieving comparable accuracy to HNSW in finding those nearest neighbors. But here's the really remarkable thing. FlatNav used 38% less peak memory than HNSW.
Wow, that's a big difference, especially when you're dealing with the kind of data volumes we see in AI today.
Absolutely. That reduction in memory means lower costs, faster processing, and the ability to handle even larger data sets. It opens up a world of possibilities for more complex and ambitious AI applications.
So this flat nav approach, while still early, is
Yeah.
showing some real promise, not just in theory, but also in those practical benchmarks.
And the implications go way beyond just nearest neighbor search. The hub highway hypothesis challenges us to rethink how we approach data organization and retrieval across all sorts of domains. Could there be other areas where we're stuck on complex hierarchies when the data itself might offer a simpler, more efficient path?
It's a call to explore, to experiment, to challenge those ingrained assumptions
Yeah.
about how we structure and access information.
Exactly. And for our listeners, actively working with ARI and vector embeddings, this research offers a valuable new tool for their toolbox. As you continue to build and refine your systems, consider experimenting with FlatNav. Explore the potential for optimizing memory usage, handling larger datasets, and maybe even improving the speed and accuracy of your search results.
It's all about finding those hidden highways within the data, those natural connections and hubs that guide us to the information we need.
And as you experiment with FlatNav, don't forget to share your findings with the community. This is a field that's changing so fast, and your insights could contribute to the development and refinement of this exciting new approach.
So, as you continue your deep dive into the world of AI and vector embeddings, remember to keep an open mind, challenge conventional wisdom, and always be on the lookout for those hidden highways within your data.
Who knows what amazing discoveries await us as we learn to embrace the inherent structure and elegance of data itself.
That's it for our deep dive, we hope. This exploration of FlatNav and the hub highway hypothesis has sparked your curiosity and maybe inspired you to explore new possibilities. In your work, keep learning, keep experimenting, and keep diving deep into the fascinating world of AI. Until next time, happy exploring.